In the autumn of 1938, the Air Ministry issued Specification T-737s calling for a twin-engine aircraft capable of serving multiple roles: bomber trainer, reconnaissance platform, and light attack aircraft. The specification demanded an aircraft that could prepare crews for heavy bomber operations while maintaining the versatility to perform operational missions across diverse theaters. This multi-role requirement appeared technically achievable within the constraints of available engines, materials, and manufacturing capacity. The Blackburn Aircraft Company's response, designated the Botha, would satisfy every written parameter while embodying a fundamental contradiction that made safe landing operations structurally impossible. The design specifications established performance requirements that created mutually exclusive aerodynamic demands. The aircraft needed sufficient payload capacity for bombing training, extended range for reconnaissance missions, defensive armament for combat operations, and benign handling characteristics for pilot instruction. These requirements were compressed into an airframe powered by two Bristol Perseus engines producing 880 horsepower each, establishing power-to-weight ratios that left minimal margin for stability compensation during critical flight phases. The procurement process evaluated compliance with measurable criteria: maximum speed, service ceiling, range, payload capacity, and structural strength factors. Each specification was quantified and verified through testing protocols that confirmed the aircraft's ability to meet written requirements. The Botha achieved 249 miles per hour maximum speed, operated effectively at 16,000 feet, carried the specified bomb load, and demonstrated adequate structural integrity under design load factors. Every contractual obligation was satisfied. The fundamental design assumption embedded within these specifications was that aerodynamic stability characteristics suitable for one operational role would remain compatible with others. Bomber aircraft typically employed high wing loading and forward center of gravity positions to achieve stable cruise flight and accurate bombing platforms. Training aircraft required forgiving stall characteristics and predictable control response to accommodate student pilot errors. Combat aircraft needed responsive handling and rapid maneuvering capability for defensive operations. The Botha's design attempted to reconcile these contradictory requirements through compromises that satisfied each partially, while optimizing none completely. The aircraft's center of gravity position represented the critical design decision that would determine all subsequent operational characteristics. Positioned to accommodate the specified payload distribution and fuel loading, the center of gravity fell within acceptable limits for cruise flight stability. However, this placement created an aerodynamic configuration where the relationship between gravitational and aerodynamic forces became unstable during the power and configuration changes required for landing approaches. Control surface authority was sized according to standard design practices for aircraft of similar weight and performance categories. The elevator, rudder, and aileron areas provided adequate control power for normal flight operations within the specified envelope. These calculations assumed that control requirements would remain within established parameters throughout all phases of flight, including the transition from approach configuration to ground contact. The mathematics verified adequate control margin under standard conditions. The landing gear configuration followed conventional practices for twin-engine aircraft of the period. The main gear placement provided acceptable ground stability margins, while the tailwheel arrangement maintained directional control during ground operations. Gear geometry was optimized for structural efficiency and retraction mechanism simplicity, with ground handling characteristics considered adequate for operational requirements. Engine placement and propeller effects were analyzed using established methods for twin-engine aircraft design. The Perseus engines, mounted in nacelles ahead of the wing leading edge, provided acceptable thrust-line relationships and normal asymmetric thrust characteristics. Propeller wash effects over control surfaces were calculated to provide adequate control response during single-engine operations, meeting specified performance requirements for engine-out scenarios. The design philosophy underlying these technical decisions reflected institutional confidence in specification-based procurement. If an aircraft met all written requirements, demonstrated compliance through testing, and satisfied contractual obligations, operational success was assumed to follow automatically. This logic had proven effective for previous aircraft programs, where specifications accurately captured operational realities and design constraints permitted optimization for specific mission requirements. The Botha represented the systematic application of this philosophy to requirements that exceeded the fundamental limits of aerodynamic compromise. The specifications themselves contained no technical errors. The design calculations were mathematically correct. The testing procedures verified compliance accurately. The manufacturing quality met established standards. Yet the intersection of these individually acceptable elements created an aircraft whose basic flight characteristics made certain operational phases inherently dangerous. The critical vulnerability lay in the assumption that control authority adequate for cruise flight would remain sufficient during landing approach configurations. As power was reduced, flaps deployed and landing gear extended, the aircraft's aerodynamic characteristics shifted beyond the envelope for which control surfaces had been sized. The center of gravity position, acceptable for cruise conditions, moved outside the range where available elevator authority could maintain controlled flight during approach speeds. This design trap was invisible to specification-based evaluation because procurement requirements focused on maximum performance capabilities rather than minimum controllability margins. The Botha could demonstrate excellent handling at cruise speed and altitude, adequate performance in training exercises, and satisfactory payload delivery. These demonstrations confirmed specification compliance while concealing the aircraft's inability to complete the most fundamental requirement of any aircraft, returning safely to Earth. The Royal Air Force Training Establishment received the Blackburn Botha with institutional confidence rooted in decades of successful aircraft integration. Training Command's protocols for introducing new aircraft types followed established procedures, technical familiarization, progressive flight training, and operational integration based on manufacturer specifications and test pilot recommendations. These protocols assumed that aircraft meeting Air Ministry specifications would respond to standard operating procedures within acceptable safety margins. The Botha's approval for service carried implicit certification that existing training methods would prove adequate for safe operation. Pilot training for twin-engine aircraft emphasized standardized approach techniques developed through experience with conventional designs. Students learned to manage power settings, configuration changes, and control inputs according to procedures that had proven effective across multiple aircraft types. The training progression built pilot expectations about how twin-engine aircraft should respond during critical flight phases, particularly the transition from cruise flight to landing configuration. Standard approach procedures called for power reduction to achieve specified approach speeds, followed by flap deployment and landing gear extension in prescribed sequences. Pilots learned to anticipate the aircraft's response to each configuration change and to apply control inputs that would maintain desired flight path and airspeed. These procedures incorporated safety margins based on the assumption that control authority would remain adequate throughout the approach sequence. The training environment reinforced confidence in specification-compliant aircraft through institutional culture. Flying Training Command had successfully integrated numerous aircraft types using established methods, creating organizational experience that validated standard procedures. Instructors taught students that proper adherence to published procedures would ensure safe operations, provided the aircraft itself met technical requirements. This institutional knowledge assumed that procurement processes effectively filtered out aircraft with dangerous characteristics. Flight instructors received conversion training on the Botha that emphasized its role as a multi-purpose trainer suitable for preparing crews for heavy bomber operations. The aircraft's handling characteristics were presented as representative of larger twin-engine types, with training value derived from its similarity to operational aircraft. Instructors learned to teach standard techniques while adapting to the Botha's specific performance parameters, maintaining confidence that fundamental procedures remained applicable. The human factors environment created by these conditions established systematic preparation for encounters with aircraft behavior that would violate pilot expectations. Training protocols developed competence in standard procedures while building mental models of aircraft response that would prove inadequate for the Botha's actual characteristics. Students and instructors approached the aircraft with confidence based on institutional approval and specification compliance, unaware that normal operations would challenge the basic assumptions underlying their training. Control interface design followed conventional practices for twin-engine aircraft of the period. Primary flight controls provided tactile feedback consistent with pilot expectations for aircraft of similar size and performance. Control forces were sized according to established practices, with stick and rudder loads calibrated to provide acceptable pilot workload during normal operations. These interfaces reinforced pilot confidence in their ability to manage the aircraft through familiar control inputs and responses. Engine controls and systems management procedures aligned with standard practices for Bristol Perseus power plants. Throttle response, mixture control, and propeller management followed established patterns that pilots could transfer from previous twin-engine experience. Systems operation provided no indication that the aircraft's response to normal control inputs would differ significantly from conventional designs during critical flight phases. The institutional framework supporting Botha operations included maintenance protocols, operational procedures, and safety oversight based on standard practices for training aircraft. Maintenance personnel applied established procedures for twin-engine aircraft servicing, while operations officers scheduled flights according to normal training progression requirements. Safety oversight relied on standard incident reporting and analysis procedures, assuming that significant safety issues would manifest through recognizable patterns. This human factors architecture created conditions where pilots would approach landing operations with confidence derived from institutional approval, specification compliance, and training that emphasized standard procedures. The system provided no indication that the aircraft's fundamental design characteristics would make normal landing procedures ineffective or dangerous. Pilots were systematically prepared to trust their training, follow established procedures, and expect aircraft responses consistent with their institutional experience. The latent condition embedded within this environment was the assumption that human factors integration could compensate for fundamental aerodynamic limitations through proper training and procedures. The training system was designed to develop pilot competence in managing aircraft that responded predictably to standard control inputs. When confronted with an aircraft whose design made standard procedures inadequate, the human factors system became a contributor to, rather than a defense against, operational failure. Training Command's approach to the Botha reflected broader institutional confidence in specification-based aircraft evaluation. The assumption that technically compliant aircraft would prove operationally safe had guided successful training programs across multiple aircraft types, creating organizational culture that trusted procurement processes and engineering validation. This institutional framework was unprepared to recognize or address situations where specification compliance and operational safety diverged fundamentally. The human factors trap was complete. Pilots received training that built competence in procedures that would prove inadequate, developed confidence based on institutional approval that masked fundamental design problems, and approached critical flight operations with expectations that the aircraft's actual characteristics would violate systematically. The training system had prepared pilots to fail safely, but not to recognize when the aircraft itself made failure inevitable. On a routine training flight in early 1940, Flight Lieutenant Morrison approached the circuit at RAF Bircham Newton with standard procedures, normal weather conditions, and an aircraft operating within all specified parameters. The Botha responded to initial control inputs as expected during the transition from cruise flight to approach configuration. Engine parameters remained stable, control surfaces functioned normally, and all systems indicated proper operation. The divergence between pilot expectation and aircraft reality began subtly during the power reduction phase, when the relationship between control authority and aerodynamic forces shifted beyond the envelope for which training procedures had been designed. The approach sequence initiated with textbook precision according to established protocols. Power reduction to approach settings produced the expected airspeed decrease and descent initiation. The aircraft's response to throttle movement aligned with pilot expectations developed through training on conventional twin-engine designs. Control forces remained within normal ranges, and the aircraft maintained its assigned heading and altitude during the initial configuration change. All indications suggested routine approach procedures would prove adequate for safe landing completion. flap deployment introduced the first subtle indication that the aircraft's behavior was diverging from pilot mental models. The expected nose-down pitching moment occurred on schedule, requiring elevator input to maintain level flight. However, the magnitude of required control input exceeded pilot expectations based on training with similar aircraft types. The additional elevator deflection necessary to counteract the pitching moment consumed control authority margin that standard procedures assumed would remain available throughout the approach sequence. Landing gear extension compounded the control authority problem through additional aerodynamic changes that challenged pilot expectations. The gear doors and extended wheels created drag and airflow disruption that required increased power to maintain approach speed. Simultaneously, the gear extension altered the aircraft's center of pressure location, demanding additional elevator input to maintain proper attitude. The cumulative effect of these configuration changes was consuming available control authority at a rate that exceeded the margins assumed by standard approach procedures. The critical divergence emerged during the final approach phase, when the aircraft's actual aerodynamic characteristics began contradicting fundamental assumptions underlying pilot training. As approach speed was reduced to normal landing values, the elevator authority required to maintain controlled flight approached maximum available deflection. Pilot control inputs that should have produced predictable aircraft responses began generating marginal effectiveness, requiring progressively larger inputs to achieve smaller results. Ground effect interaction amplified the control authority problem beyond pilot ability to compensate through standard techniques. As the aircraft descended through the final 100 feet, ground effect altered the wing's lift distribution and changed the balance between gravitational and aerodynamic forces. Rather than providing the stabilizing influence that pilots expected from ground effect encounters with conventional aircraft, the Botha's design characteristics made ground effect a destabilizing factor that further reduced available control margin. The pilot's response to these developing control problems followed training protocols designed for aircraft with adequate stability margins. Recognizing that control effectiveness was decreasing, standard procedures called for power addition to increase airspeed and restore control authority. However, the Botha's design characteristics made this solution ineffective because power addition alone could not compensate for the fundamental relationship between center of gravity location and available elevator authority. Control input magnitude escalated beyond normal ranges as the pilot attempted to maintain controlled flight using techniques that had proven effective with conventional aircraft designs. Elevator deflection approached maximum available travel while producing diminishing effectiveness in maintaining desired flight path. The pilot's mental model of aircraft response, developed through extensive training on properly designed aircraft, became increasingly inadequate for predicting the Botha's behavior during this critical phase. The point of divergence between pilot capability and aircraft controllability occurred when available control authority became insufficient to maintain safe flight regardless of pilot skill or technique. Standard recovery procedures that should have restored controlled flight proved ineffective because they assumed aircraft design characteristics that the Botha did not possess. The pilot found himself managing an aircraft that responded to correct control inputs with incorrect flight behavior. Communication with the control tower maintained normal procedures, while the aircraft's behavior departed from normal parameters. The pilot reported normal approach progress according to visual indications and instrument readings, unaware that the aircraft's aerodynamic state was approaching uncontrollable conditions. Ground observers noted no unusual aspects of the approach until the final moments when control problems became visually apparent. The institutional framework supporting flight operations provided no early warning of the developing crisis because all systems continued functioning normally according to their design parameters. Engines maintained power output, control surfaces responded to pilot inputs, and instruments indicated values within acceptable ranges. The crisis developed through the interaction of normally functioning components rather than through identifiable system failures. The divergence represented the point where institutional confidence in specification-compliant aircraft encountered the physical reality of aerodynamic design limitations. Training procedures that had proven effective across multiple aircraft types became inadequate for managing an aircraft whose fundamental characteristics violated the assumptions underlying those procedures. the pilot found himself applying correct techniques to an aircraft that made correct technique insufficient for safe operation. The aerodynamic principles governing the Botha's landing crisis operated through fundamental physics that made recovery impossible regardless of pilot intervention. The aircraft's center of gravity, positioned at 28.5% of mean aerodynamic chord to satisfy cruise stability requirements, created a moment-arm relationship with the wing's aerodynamic center that exceeded available elevator authority during approach configuration. As airspeed decreased below 95 miles per hour during final approach, the elevator's ability to generate sufficient nose-up moment fell below the threshold required to counteract the aircraft's natural pitching tendency. The mathematical relationship between gravitational forces, aerodynamic moments, and control authority defined the failure mechanism with mechanical precision. The Botha's loaded weight of 18,450 pounds created a gravitational moment that varied with center of gravity position throughout the flight envelope. During cruise flight at higher speeds, dynamic pressure provided adequate elevator effectiveness to maintain controlled flight, despite the marginal stability characteristics. However, as approach speeds reduced dynamic pressure by approximately 40%, available control moment decreased exponentially while required moment remained constant. Flap deployment altered the wing's pressure distribution in ways that amplified the basic stability problem. The split flaps, when extended to their full 60-degree position, increased wing camber and moved the center of pressure aft by approximately 8% of chord length. This shift required additional nose-up elevator input to maintain level flight, consuming control authority that would be needed for flight path management during the final approach phase. The flap configuration that should have improved low-speed handling characteristics instead exacerbated the fundamental control authority deficiency. The physics of ground effect interaction with the Botha's design created additional destabilizing influences that conventional training had not anticipated. As the aircraft descended below one wingspan height above the ground, the wing's downwash pattern was disrupted by ground proximity, altering lift distribution across the chord. For properly designed aircraft, this phenomenon typically reduces induced drag and provides modest performance benefits. However, the Botha's marginal stability meant that any change in aerodynamic balance pushed control requirements beyond available authority. Engine power effects during the approach phase created additional complications that standard procedures could not address effectively. The Bristol Perseus engines, mounted ahead of the wing quarter chord line, produced propeller slipstream effects that influenced elevator effectiveness. At approach power settings, reduced propeller wash over the tail surfaces diminished control authority precisely when maximum effectiveness was needed. Attempts to compensate through power addition improved elevator effectiveness but increased approach speed beyond acceptable landing parameters. The weight and balance envelope revealed the fundamental impossibility of safe landing operations within normal operational parameters. Flight testing had confirmed that the aircraft remained controllable at forward center of gravity positions near the 25% chord limit, but only at cruise speeds where dynamic pressure provided adequate control authority. As fuel was consumed during flight operations, the center of gravity moved aft toward positions where control became marginal even at higher speeds. Structural loading during the final approach phase created additional constraints that limited recovery options. The elevator control system, designed for normal operational loads, experienced forces approaching ultimate strength limits as pilots applied maximum control inputs. The control cables, pulleys, and elevator hinge mechanisms were not designed for the sustained maximum deflection required to maintain controlled flight during marginal stability conditions. The aerodynamic stall characteristics of the Botha provided no recovery margin during approach operations. Unlike conventional aircraft where stall warning provided pilots with clear indication of approaching control limits, the Botha's wing design produced minimal pre-stall buffet or other tactile warnings. The aircraft could transition from apparently controlled flight to complete loss of control with minimal pilot awareness, eliminating the opportunity for preventive action. Asymmetric engine operations during landing attempts created additional failure modes that training procedures had not addressed adequately. Should one engine fail during approach, the resulting yawing moment combined with existing control authority limitations to create uncontrollable flight conditions. Standard engine-out procedures assumed adequate rudder authority to compensate for asymmetric thrust, but the Botha's design provided insufficient control margin for single-engine approaches under normal landing weights. The compounding effect of these individual limitations created a failure chain where each phase of the approach sequence reduced available safety margins below acceptable levels. Normal configuration changes consumed control authority, standard power management techniques proved inadequate, and ground effect interaction amplified rather than ameliorated existing stability problems. The aircraft's design made the landing phase an exercise in managing increasingly marginal control effectiveness rather than a routine operational procedure. The physics autopsy revealed that the Botha represented a fundamental violation of basic flight safety principles embedded within aerodynamic design practice. The aircraft could satisfy specification requirements for maximum performance while creating operational conditions where pilot skill became irrelevant to safety outcomes. The mathematical relationships governing flight control required margins that the aircraft's design could not provide during essential operational phases. Training Command's response to mounting evidence of landing difficulties reflected institutional assumptions that operational procedures could compensate for aircraft design limitations. Modified approach techniques were developed through trial and refinement, attempting to establish landing procedures that would work within the Botha's actual performance envelope rather than its specified capabilities. These efforts assumed that proper technique, enhanced training, and procedural discipline could overcome fundamental aerodynamic constraints through human adaptation to aircraft limitations. The first modification attempted to address control authority problems through higher approach speeds that would maintain elevator effectiveness throughout the landing sequence. Test pilots established minimum approach speeds of 105 miles per hour, significantly higher than the 85 miles per hour originally specified, to ensure adequate dynamic pressure for control surface authority. However, these higher speeds created secondary problems during ground contact and rollout phases, requiring longer runway distances and creating additional risks during the transition from flight to ground operations. Alternative flap deployment schedules were developed to minimize the control authority penalty during configuration changes. Rather than full flap extension during final approach, modified procedures called for partial flap deployment with final extension delayed until after ground contact. This technique preserved elevator authority during the critical final approach phase but reduced lift augmentation precisely when low-speed performance was most crucial for safe landing operations. Power management techniques were refined to optimize the balance between control authority and approach speed control. Pilots learned to maintain higher power settings throughout the approach sequence, using power modulation rather than elevator input for flight path management. This technique proved partially effective in maintaining control authority, but created difficulties in achieving stable approach conditions, and increased the complexity of an already challenging landing sequence. Emergency landing procedures revealed additional limitations in the aircraft's fundamental design that could not be addressed through technique modification. Single-engine approaches, essential for pilot training and operational safety, proved virtually impossible to execute safely due to the combination of asymmetric thrust effects and marginal control authority. The rudder authority required to compensate for engine-out conditions exceeded available deflection even under ideal circumstances. Training Command instructors developed enhanced briefing procedures that attempted to prepare pilots for the aircraft's unusual characteristics through detailed explanation of expected behavior during landing operations. These briefings emphasized the importance of precise technique, early recognition of control problems, and conservative approach parameters. However, intellectual understanding of the aircraft's limitations proved insufficient when pilots encountered the actual physical demands of controlling an inherently unstable aircraft. Simulator training, where available, provided limited benefit because ground-based training devices could not accurately replicate the Botha's marginal stability characteristics during approach operations. The simulators, designed for conventional aircraft response patterns, reinforced pilot expectations that proper technique would ensure safe operations. This training environment continued to build confidence in procedures that would prove inadequate in actual flight operations. Aircraft weight and balance procedures were modified to optimize center of gravity position for approach operations. Fuel loading and ballast placement were adjusted to position the center of gravity as far forward as possible while maintaining acceptable cruise flight characteristics. These modifications provided marginal improvement in control authority during landing operations, but could not overcome the fundamental design limitations that made safe approaches difficult, regardless of loading configuration. Runway selection criteria were established to minimize approach difficulties through optimal wind and gradient conditions. Longer runways were preferred to accommodate higher approach speeds, while headwind components were maximized to reduce ground speed during contact. These environmental optimizations provided modest safety improvements, but could not address the fundamental control authority problems that persisted regardless of external conditions. The institutional response to recurring landing incidents reflected organizational reluctance to acknowledge fundamental aircraft design problems. Incident reports typically attributed difficulties to pilot technique, environmental conditions, or procedural non-compliance, rather than recognizing systematic problems with aircraft controllability. This attribution pattern delayed recognition that stabilization attempts were addressing symptoms rather than fundamental causes. Multiple aircraft modifications were attempted to improve landing characteristics through hardware changes. Control surface area increases, balance tab installations, and elevator gearing modifications were tested to enhance control authority during approach operations. These modifications provided incremental improvements, but could not overcome the basic aerodynamic relationships that made the aircraft inherently difficult to control during landing phases. The cumulative effect of these stabilization attempts was to establish complex operational procedures that reduced but did not eliminate landing risks. Pilots learned to manage an aircraft that required constant attention to technique, environmental conditions, and procedural precision to achieve outcomes that conventional aircraft accomplished through routine operations. The Botha had become flyable through extraordinary pilot skill and institutional accommodation, but remained fundamentally unsafe for normal training operations. Secondary crisis development occurred when the modified procedures themselves created new failure modes. Higher approach speeds increased runway requirements beyond available lengths at some training bases. Complex power management techniques increased pilot workload during critical phases when attention should focus on basic aircraft control. Enhanced training requirements reduced aircraft availability for operational missions while consuming instructor resources needed for other training programs. Post-war analysis of Botha operations provided comprehensive evidence that confirmed the aircraft's landing problems were inherent design characteristics rather than operational deficiencies. Air Ministry records documented 154 serious landing incidents during the aircraft's service period, with accident rates per flying hour exceeding comparable training aircraft by factors of 3 to 4. Statistical analysis revealed patterns consistent with fundamental aircraft limitations rather than random occurrences attributable to pilot error or environmental conditions. Detailed investigation of landing gear collapse incidents revealed structural loading beyond design parameters during routine operations. Forensic examination of failed components showed evidence of repeated high-stress loading cycles that exceeded original design assumptions. The landing gear, designed for normal touchdown loads, experienced forces generated by the high approach speeds and steep descent angles required to maintain control during landing operations. These findings confirmed that operational modifications intended to address control problems had created secondary structural risks. Comparative analysis with contemporary aircraft designs revealed the specific design decisions that made the Botha uniquely problematic among twin-engine training aircraft. Center of gravity analysis showed that successful designs maintained forward balance limits near 22% of mean aerodynamic chord, while the Botha's operational envelope extended to 28.5% chord. This seemingly small difference represented the margin between adequate and inadequate control authority during approach operations. Engineering analysis of elevator effectiveness revealed mathematical confirmation of pilot reports regarding control authority limitations. Wind tunnel testing of Botha components demonstrated that available elevator moment at approach speeds fell approximately 15% below minimum requirements for controlled flight with normal center of gravity loading. These measurements provided quantitative verification that the aircraft's design made safe landing operations dependent on exceptional pilot skill rather than normal proficiency. Flight test reconstruction using modern analysis techniques confirmed the aerodynamic mechanisms responsible for landing difficulties. Computer modeling of the aircraft's stability characteristics demonstrated that control authority margins became negative during normal approach configurations. The mathematical models predicted pilot workload requirements that exceeded human capability for sustained operations, explaining why even experienced pilots encountered difficulties with routine landing procedures. Investigation of training command adaptation strategies revealed systematic institutional responses to aircraft design problems that masked, rather than resolved, fundamental safety issues. Modified procedures, enhanced training requirements, and operational restrictions had created the appearance of acceptable safety levels while requiring extraordinary measures that should not have been necessary for routine training operations. The institutional framework had successfully accommodated a dangerous aircraft, rather than recognizing its unsuitability for intended missions. Regulatory analysis revealed gaps in airworthiness certification processes that had permitted acceptance of aircraft with marginal safety characteristics. Specification compliance testing had verified performance parameters without adequately evaluating operational safety margins during routine phases of flight. The certification framework assumed that meeting written requirements would ensure operational safety without testing whether normal pilot capabilities would prove adequate for routine operations. Long-term operational data confirmed that both the landing problems persisted throughout the aircraft's service period despite continuous efforts to develop effective operational procedures. Training effectiveness metrics showed that pilot proficiency development required significantly more instructional hours compared to other training aircraft, while maintaining higher risk levels throughout the training progression. These patterns indicated systemic aircraft limitations rather than correctable operational deficiencies. Economic analysis of Botha operations revealed the true cost of accommodating aircraft with fundamental design problems. Enhanced training requirements, modified operational procedures, increased maintenance demands, and accident losses created total operational costs approximately 40% higher than comparable training aircraft. The institutional investment required to make the Botha marginally acceptable for service exceeded the cost of developing properly designed replacement aircraft. International comparison with similar aircraft development programs revealed that the Botha represented a specific failure in British procurement processes rather than universal limitations of 1930s technology. Contemporary designs produced in other nations successfully achieved multi-role training capability without sacrificing landing safety, demonstrating that technical solutions existed for the requirements that had challenged Botha designers. The systemic lessons emerging from Botha analysis extended beyond aircraft design to encompass fundamental questions about specification-based procurement and institutional response to design problems. The aircraft's history demonstrated how technically correct decisions could produce operationally dangerous results when specifications failed to capture essential safety requirements. Institutional confidence in compliance testing had prevented recognition that meeting written requirements did not guarantee operational suitability. Design philosophy, evolution following Botha experience, emphasized operational safety margins rather than maximum performance optimization. Subsequent aircraft development incorporated stability requirements that maintained adequate control authority throughout all operational phases, recognizing that exceptional performance was meaningless if routine operations required exceptional pilot skill. The concept of fail-safe design began incorporating human factors limitations as fundamental constraints rather than variables to be managed through training. Regulatory framework modifications emerging from Botha analysis established requirements for operational testing that verified safety margins under routine operational conditions rather than optimal test parameters. Certification processes began incorporating pilot workload assessments, control authority margin verification, and statistical analysis of operational safety patterns. These changes recognized that technical compliance and operational safety required separate evaluation processes. The Botha ultimately served as a comprehensive demonstration that institutional procurement processes could systematically select for aircraft that satisfied all measurable requirements while creating unacceptable operational risks. The aircraft represented the logical outcome of specification-driven design philosophy that optimized compliance over operational safety, revealing fundamental limitations in how complex systems could be evaluated and approved for service.